Hey everyone, welcome back. So in this video, we're going to cover our first theoretical discrete probability distribution, which is the binomial distribution. So a probability distribution is referred to as theoretical when the mathematical properties of its random variable are used to produce its probabilities. So let's get started. So the binomial probability distribution is a distribution that gives the probability of X successes in N trials in a process that meets the following conditions. So the binomial distribution will have a trial that only has two possible outcomes, a success or a failure. If you recall in the previous video, when we talked about discrete random variables, there are two possible outcomes. One could be buying a product or not buying a product. There could be a situation where we're winning or we're not. So it doesn't necessarily mean a positive or a negative thing. So you want to be careful in how you assign what is a success and what is a failure. A good rule of thumb to remember is that the success is the probability of something happening that you're looking for, and the failure is the complement of it. So the second condition here is that there's a fixed number of identical trials. The trials are independent of each other. Recall that independent events mean that they don't affect or influence one another. So in addition, the process of your experiments must be consistent in a way you generate failures and successes. Successes are denoted by the letter P and remain constant from trial to trial. Then 1 minus P, which is our complement rule, is Q. That's the probability of failure. Here, we're just making sure that we understand how to denote a success by the letter P and denote a failure, which is the letter Q. Some examples of when we use the binomial distribution would be when a manufacturing company inspects its products and classifies them as either defective or acceptable. In the case, our success would be the defective parts because that's what we're looking for. And then failure would be the acceptable parts. So you can see that success and failure do not necessarily mean negative or positive things, but it's rather what is our event of interest. So another example would be a firm bidding on a contract and whether they win the contract or not. So in this case, winning the contract is my success and not winning the contract is my failure. So another example would be a marketing research firm that sends out a survey to potential customers and asks them if they're going to buy or not buy the product. So in this case, yes, I will buy is my success and no, I will not buy is my failure. So let's review the counting rule next. So the counting rule for combinations is a method for counting the number of ways that our binomial event can occur. You will see this when we work through specifically the binomial distribution formula. So N is our number of trials that we have. X is the random variable interest that we're trying to find out about. So note, the order of events really does not matter. So using the counting rule for combinations makes it easier for us to determine how many options there are as opposed to listing out every possible combination of event like we did earlier with that ice cream example in chapter 4. So here, the exclamation mark refers to a factorial. So this is a formal way of representing a factorial, but you might want to check your calculator for the factorial button so you know where to find it and how to calculate a factorial of any number. So a factorial is when we multiply the number by every number below it down to 1. So for instance, if we had the factorial of 5, then that just means we're going to take 5 times 4 times 3 times 2 times 1. So just as an FYI, the factorial of 0 is 1 by definition. So this is what our binomial formula looks like. P of X, recall that this means the probability of X successes in our set of trials. So N is the number of trials or sample size, X is the number of successes in the sample, and then P is probability of success, and then Q is the probability of failure or the complement of P. So in our formula here, we will take the factorial of N and divide by the factorial of X times the factorial of N minus X. Once we have calculated the left side of the equation, then we're going to multiply it by P to the power of X, and then the last step is to multiply that result by Q to the power of N minus X. So just talking through the calculation probably didn't help much. So let's walk through a specific example. So 35% of the population supports a new regulation. If a random sample of 10 voters is polled, what is the probability that exactly 3 of them support the proposition? We know this is a binomial distribution because there are only 2 options. the voters are either for the regulation or they're against it. In this case, what we are interested in is exactly 3 of them support the proposition. So our success here is the support of the new law. So when we write it out, we're looking for the probability that exactly 3 people support this new law. So our sample size, which is given to us, is the 10 voters. So n equals 10, and the probability of success in this case is the probability of support, or 35%. So we'll want to take the 35% and change it into a decimal format to represent our p. So let's go ahead and start with the left side of the equation. So our n equals 10, so I'll plug that into our numerator. Here is my x that I'm interested in, so that's 3, so I'll plug that in. And then we'll take 10 minus 3 inside of the parentheses. Our probability of success was 0.35, so I'll plug that in for p, and then x is the exponent, so that ends up being 0.35 to the power of 3. Now q is my complement of success or my failure. So that's 1 minus p, or 1 minus 0.35, and that's how we get 0.65 here. And then we're going to take that to the power of n minus x, or 10 minus 3. So now that we have all of our numbers plugged into the formula, we're going to use our calculator to solve for this. But we really need to break it down into parts because getting the correct order in your calculator can be tricky. So we'll start with the right and the exponents first. So we'll take 0.35 to the power of 3, and we get 0.0429. Then we'll take 0.65 to the power of 10 minus 3, or 7, and we get 0.049. So now with our counting rule on the left side of the equation, we're going to calculate it this way. So factorials can return really large numbers. So we're going to do it in some steps here and not list out each big number on the way. So first, in your calculator, you're going to input 10 and you're going to click on the factorial button. So on a scientific calculator, it should be the button with the N with the exclamation mark. Then you're going to click on the divide button and enter 3, and then you're going to click on the factorial button again. The last step is we're going to hit the divide button again, and then we're going to enter 7 and the factorial button. So finally, we're going to click on the equals button, and you should get 120 as shown here. If you did not get 120 as you are following along with me, you may have had an input issue. So rewind or pause the video and give it another try. So we'll then multiply all 3 of these numbers together, and we get 0.2522. So there's a 25.22% chance that exactly 3 out of the 10 voters will support the new regulation. So fortunately, there's an Excel option for finding the binomial distribution. So on the last slide, when we used the binomial formula, it only gave us the probability of an exact number of 3. Often though, we may be looking at different ways, such as up to a number or greater than equal to a number. So the binomial distribution function in Excel consists of 4 fields. So inside the parentheses of the function, we'll put the number of successes in our trials. So number underscore S means our X value. The trials are the number of independent trials that we have. So based on our formula, that's the N or sample size. Probability underscore S is the probability of success on each trial. So that is our P. And then the cumulative just tells us what we're looking at. So if we type in true, that means the probability of whatever number of successes we're looking at up to that value. If we input false, that just means we're looking for an exact number like we just did on the last slide. So here's a visualization of the binomial distribution. So if we plotted the probabilities in our voter's story example, it would look something like this. So in Excel, when we're talking about cumulative, it's going to read the probabilities starting from left to right. So we'll add up the probabilities depending on what our X is. If we're not doing cumulative, so you type in false in Excel, it's going to look for the probability at an exact number. So you could see the 0.2522 here for the 3 bar. So over the next 3 slides, we're going to walk through the binomial dist function arguments or the inputs for the same voter example. This slide is the exactly 3 scenario we have already calculated, but we're going to use this as a way of validating the calculation we did earlier. So we want to know the probability that X is exactly 3 or P of X equals 3. Since we want to know the exact probability when X equals 3, we will use false for the cumulative argument. We will plug in a 3 as the number of successes, 10 for the number of trials since we had 10 voters. We will then enter 0.35 for the probability of success since 35% of the population supports the new regulation. And the Excel formula outputs 0.2523, which as you can see matches what we did before. So let's change up the story now and assume we want to know the probability of 3 or fewer. So we want to know the probability that x is 3 or fewer, or p of x is less than or equal to 3. So you could say 3 or fewer or less than 4. These both mean the same thing. Since we now want to add up the probabilities for 1, 2, and 3, we're going to use true for the cumulative argument. So again, we will plug in 3 as the number of successes, 10 as the number of trials, 0.35 for the probability. So this does not change from the prior example. The only change is the true argument for cumulative. And the Excel formula outputs 0.5138. So in our last scenario here, we want to know the probability of more than 3. So now this is tricky because the cumulative argument works from left to right or up to the number of successes. However, we can use the complement rule here to get what we want. We will use the exact same inputs as we did on the last slide for 3 or fewer, and then just apply the complement rule. So we're going to take 1 minus 0.538, and we get 0.4862. Okay, so let's wrap it up now with another practice problem. So for question 5.30, we were given that a random variable follows a binomial distribution with a probability of success is 0.45 and the number of trials is 11. So we're going to go ahead and plug in 11 for n and 0.45 for p, and then we know that q is the complement of p, or 1 minus 0.45, and we get 0.55. So as we did before, we're going to use Excel for this practice problem. So in A, we want to know the probability of exactly one success. So the event of interest here is P of X equals 1. So we're going to plug in 1 for our X, 11 for our N, 0.45 for our probability of success. We know that we want the probability of exactly 1, so we won't be adding up the probabilities. So that means we'll use false for cumulative. We plug that into our Excel formula and we get 0.0125. So in B, we want to know the probability of 4 or fewer successes. So in this question, the event of interest is P of X less than or equal to 4. So we will plug in 4 for our X, 11 for our N, 0.45 for our probability of success. Now we do want to add up the probabilities for 1, 2, 3, and 4. So we will input true for cumulative. We plug that into our Excel formula and we get 0.3971. So now the last problem in C here, we want to know the probability of at least 8 successes. So the event of interest is P of X greater than or equal to 8. So this is where you really must watch out for what X you use here. So we know that the binomial function counts the probabilities up to the X number. Therefore, if we used 8 here for the X, then took the complement, we'll be losing the probability of exactly 8 in the total. This is because the function will be telling us the cumulative probabilities up to 8. So the complement of that is starting at 9. And that's not what we want here. So P of X is greater than or equal to 8 is actually 1 minus the probability of X is less than or equal to 7. So we are going to plug in 7 for our X, 11 for N, 0.45 for our probability of success, and true for cumulative, and we get 0.9390. We take 1 minus 0.9390, and we get 0.0610. So let's wrap this up and talk about the mean and standard deviation for a binomial distribution. So the expected value or mean in a binomial distribution is simply n times p. N is our sample size or the number of trials, and p is the probability of success. The standard deviation is n times p times q, and then we take the square root of the whole thing. So we're going to take our sample size multiplied by the probability of success times the probability of failure and then square root it. So let's do a practice problem. So on problem 5.39, Walmart has tracked customers who visit its website and determined that 37% will make a purchase from the website within 6 months of their first visit. 8 people who visit the website are selected at random as a sample. In A, determine the expected number in the sample who will make a purchase within 6 months. So here are the formulas we just discussed. So we're going to plug in the right values into the right place. So we're going to take 8 for N, which is the number of people that visited the website, and 0.37 for the probability that a customer makes a purchase, and we get 2.96 for the expected value. So in B, we want to calculate the standard deviation of who will make a purchase. So we'll plug in 8 for N, 0.37 for P, 0.63 for Q, which is the complement of P, or 1 minus 0.37. We'll take the square root of that, and we get 1.3656. Well, that wraps up this video on the binomial distribution. In our next video, we'll wrap up chapter 5 and learn about the Poisson probability distribution.